Hi students, my name is Nitesh Shet. I am from Honora. So last class we discussed about a topic from 10th standard, that is real number system. In real number system we already discussed about Euclid's division lemma, fundamental theorem of arithmetic and theorem 1.3. So let us move on to the next concept, that is some other theorems on real numbers. That is, so we already learned up to theorem 1.3. So here we are just discussing about theorem 1.5, 1.6 and 1.7. So this is the last part of the real number system. That is a topic from 10th standard. So let us move on to the theorem 1.5. Theorem 1.5 states that let x be any rational number whose decimal expansion terminates. So we already learned in a last previous standards, that is what is the terminating decimals, what are the non-terminating decimals. Here we are just taking terminating decimals. Let x be any rational number whose decimal expansion terminates. Then x can be expressed in the form of p by q. P and q are co-primes, and this the prime factorization of q can be expressed in the form of 2 raised to n into 5 raised to m, where n and m are non-negative integers. So quite bigger statement is there. So I will write one by one. So let us discuss about this statement. Let x be any rational number whose decimal expansion terminates. Whose decimal expansion terminates. Then x can be written in the form of p by q. P and q are co-primes. P and q are co-primes, and the prime factorization of q is of the form 2 raised to n and 5 raised to n, where n and m are non-negative integers. So quite bigger statement is there. So bigger also simpler statements we have to understand in simpler way. So let x be any rational number whose decimal expansion terminates. So rational number means there is a terminating decimals also there and non-terminating decimals also there. So our confusion is clear, that is let x be a rational number whose decimal expansion always terminates here. We are just taking terminating decimals in this statement. So our confusion is clear. So next, then x can be written in the form of p by q. So x be a rational number means it always expressed in the form of p by q. P and q are integers. So also q is not equal to 0 and HCF of pq is equal to 1. So that means p and q are co-primes. Then and the prime factorization, the very important part of this statement is this one, that is the prime factorization of q, that is denominator, the prime factorization of denominator is can be of form 2 raised to n, 5 raised to m, where n and m are non-negative integers. That means any rational number x is a rational number which decimal expansion terminates. That means, so that denominator, the p by q, can be expressed in the form of 2 raised to n into 5 raised to m. So where n and m are non-negative integer. So this is the statement of theorem 5. So let us move ahead to the theorem 1.6. It's just the inverse of 1.5. So we have to take the inverse. So here we can part this theorem 1.5 into two parts. So up to this is a one part, and from this to this is another part. So we have to invert that one. So we have to invert these two parts. So this part into upper side and this part into the lower side. It will be the inverse of theorem 1.5 or the statement of theorem 1.6. So let us write the statement of theorem 1.6. So theorem 1.6. So we have to just start with this. Let x is equal to p by q. P and q are co-primes. P and q are co-primes, and the prime factorization of q is of the form 2 raised to n and 5 into 5 raised to m, where n and m are non-negative integers. Then, so let us come to this completes this part, and let us go to the next part here. Then x has decimal expansion which is terminates. Yes. So simply we can write the inverse of theorem 1.5. So just bifurcating theorem 1.5 into two parts. So here I will write the second part as x has decimal expansion which is terminates. So here x be any rational number is there. Why I doesn't take here? So that is simply I will take x is equal to p by q here. So that means x is equal to p by q means x is equal to rational number. We are always understanding from this statement. So as x is a rational number. So I didn't mention in second time. So here, so it's a theorem 1.5 and theorem 1.6. The theorem 1.6 tells us that, so when x is a rational number, x is equal to p by q, p and q are co-primes and p and q are integers. So and the prime factorization of q is of the form 2 raised to n into 5 raised to n. If we write a denominator in the form of 2 raised to n and to 5 raised to m, that means the rational number always terminates. So the statement tells us that when we are able to write the denominator in the form of 2 raised to n into 5 raised to m, that means x is always a terminating decimals. X be a rational number and it's always having a decimals which always terminates. If this cannot be in the form of 2 raised to n into 5 raised to m, that means it will be in the form of the x is a non-terminating decimals. So it's a theorem 1.7. Very simple theorems are there. So theorem 1.5, the inverse of theorem 1.5, theorem 1.6 is the negative of this theorem 1.6 is the theorem 1.7. So theorem 1.7 is discussed in the after some taking examples. So I hope you already understood about theorem 1.5 and theorem 1.6. So I will write theorem 1.7 also here. So we will compare about theorem 1.5 and 1.6. That is just theorem 1.6 is the inverse of theorem 1.5. So then we have to write theorem 1.7. So theorem 1.7 is quite simple. So when the denominator, the prime factorization of denominator cannot be expressed in the form of 2 raised to n and 5 raised to m, that is not the x as present in the expression which does not terminate. It's a non-terminating decimals. It is let x is equal to p by q. P and q are co-primes. P and q are co-primes, and the prime factorization of q cannot be of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers, then x has decimal expansion non-terminating. Here, when the prime factorization of denominator can be expressed in the form of 2 raised to n into 5 raised to n, then the rational number is terminating. Here, when the denominator cannot be expressed in the form of 2 raised to n into 5 raised to m, that means this rational number cannot be expressed in the form of terminating decimals. That is, this decimal expansion is not terminating. So let us discuss this theorem by taking some of the examples. So the problem 1, so we are taking example 1 as 3 by 8. So here we have to represent this denominator is in the form of 2 raised to n and 3 raised to m, where n and m are positive integers. There is no negative integers. So just here 8 can be represented in the form of 2 raised to 3. So 3 by 2 raised to 3. So I will written it, but the denominator can be expressed in the form of 2 raised to n into 5 raised to m here. So I will just multiply and divide it by 5 raised to 3 in this rational number. So 2 raised to 3 into 5 raised to 3. So I will multiply 5 raised to 3 to the denominator. So likewise I have to multiply to the numerator also. So what we get here? So 2 raised to 3 into 5 raised to 3. So we already know about the algebraic identity, that is a raised to m into b raised to m is equal to a into b whole raised to m. So here, so we have to apply the algebraic and identity in the denominator. So that means 2 into 5 raised to 3 here. That means here 3 into 5 means 5 raised to 3 is equal to 125. Here what we get? So 3 into 125 means 375 divided by 10 raised to 3 here. So 375 divided by 1000 is equal to 0.375. So that means it's a terminating decimal. So just recall about theorem 1.5. So x is a rational number, 3 by 8, x is a rational number. So it can be expressed. So the denominator can be expressed in the form of 2 raised to 3 into 5 raised to 3. So that means that rational number is a terminating decimal. So I hope you understood this one. So let us take another example. (13 divided by 125). So 13 divided by 125 can be written as a 13 by 5 raised to 3 here. So 13. So we have to express in the form of 2 raised to n into 5 raised to m. So 5 raised to m is already is there, and we have to multiply 2 raised to 3 to the numerator and the denominator. So that is 2 raised to 3 divided by 2 raised to 3 into 5 raised to 3. So is equal to, so from the algebraic identity we can solve here 10 raised to 3. So and 13 into 8 here. So is equal to 104 divided by 1000 is equal to 0.104. So here also we can recall about theorem 1.6. So theorem 1.6 told us that the x can be written in the form of p by q when the denominator can be expressed in the form of 2 raised to n into 5 raised to m. That means n and m are non-negative integers. So the x, that rational number, is a terminating decimal number. So we already proved it. So let us take one last example. 7 divided by 180. Sorry, we can take 80. So 7 by 80. That means 7 by, so we can write 80 as a 16 into 5. So check whether value is disturbed here. No. 16 into 5 is equal to 80. Then 16 can be written as 2 raised to 4. 2 raised to 4 into 5. So because we can write it in a 2 raised to n into 5 raised to m. So here 2 raised to 4 is there, but 5 is there. We have to equate. So it is 2 raised to 4 and 5 raised to 4 we want. So that we have to multiply 5 raised to 3 to the numerator and also to the denominator. That means 7 into 5 raised to 3 divided by 2 raised to 4 into 5 into 5 raised to 3. So it can be written in the form of 7 into 125 divided by 2 raised to 4 into 5 raised to 4 is equal to, so it will be 875 divided by, so 2 into 5 whole raised to 4. From that identity, a raised to m into b raised to m is equal to a into b whole raised to m is equal to 875 divided by 10 raised to 4 is equal to 875 divided by 10,000 is equal to 0.0875. 0.0875 is the answer. So also we can recall about theorem 1.6, that is, let x be the p by q, p and q are co-primes, and then the factorization can be expressed in the form of, the denominator of prime factorization can be expressed in the form of 2 raised to m into 5 raised to m. So then the rational number is terminating. It's also a terminating decimal number. So I hope you understood about theorem 1.5, theorem 1.6, theorem 1.7. Just try to write theorem 1.5, 1.6 and 1.7 without help of your notes, so you can memorize. You have to think out your own way. So by this some methods I have told in this video. So let us take any other example to solve this problems. So this is the concluding part of this real numbers. So I hope you understand all the concepts about real numbers. We already discussed about real numbers and Euclid's division lemma, their uses, their applications and some of the problems, and then we are discussing about fundamental theorem of arithmetic and their problems. So then we have discussed about theorem 1.3 and 1.4 and theorem 1.5, 1.6 and 1.7. So these are all about the real numbers. So thank you one and all. So just try to think out mathematics in your home. Be safe and stay home. Thank you one and all.